Everyone, welcome to my void. What's up? Nah. Um, so today I just wanted to do a simple video where I'm essentially going to try to recall from memory what we've done so far regarding eigenvalues and eigenvectors. This is going to help me, and once again with this channel, I'm just as much trying to like teach you like the outcome as much as, that process, as much as showcasing the process of learning itself. So with that, let me try and recall. So this whole thing started with my generated like linear algebra learning exercises. And number six was computing eigenvalues and eigenvectors of a symmetric matrix. And then optionally do implement the power iteration method for the dominant eigenvalues. Yeah. And as I went down that rabbit hole, essentially in the exercise itself, I was in the clear to just use NumPy and move on with this, but I decided to actually, are my glasses? Okay, yeah. Sorry. But I'm like staring at myself. I'm like, are my glasses messed up? Anyways, um, in the exercise itself, I was asked to just use NumPy. And as is noted previously in this channel, I prefer to, go a little bit extra and take challenge. So I went down this rabbit hole of how would you actually get these eigenvalues and eigenvectors yourself, which led me to try and understand what even eigenvalues and eigenvectors are, which took me a stupid amount of time, I feel, but I'm pretty sure I understand them. So essentially, eigenvalues and eigenvectors of a matrix um, are vectors that when you take the product of that matrix and that vector, um, and you can see that matrix as a linear transformation in space. Um, if you take, if you apply that transformation to the eigenvector, the results will be the same eigenvector scaled by some factor, right? And that factor is called the eigenvalue. So essentially, you take this vector, you transform it, and after it's transformed, it's still in the same vector space as the original vector, essentially, right? It'll have the same origin and everything. It's just whether or not it will be in the same direction or whether it's stretched or shrunk. And that's defined by the eigenvalue, right? It's a pretty straightforward concept in terms of what they are. In terms of how you calculate them, there's a few different ways. Uh, the way we were instructed to do in the exercise was symmetric matrices. And I think in problems where you get to construct and define things, that's the best way to do it because symmetry makes life easier in that some of the steps that you have to do can become computationally less problematic. Uh, and it's computationally easier, and it's also easier from a numerical stability perspective if you back transform um, a matrix or the vectors or whatever. I actually don't understand exactly what the concept of back transforming and the residuals are, but I think that has to do with later points in time when I do things like PCA or SVD. I think that's where this concept of you don't want to blow up your residuals and back transforming really comes into play. So that's where symmetry helps. Now, in terms of the steps of how you actually do it, essentially there is something called the QR algorithm or the QR factorization method, where essentially we take the matrix and we transform it. Now, for a symmetric matrix, we can do Householder reflections to get a tridiagonal. Otherwise, we can do Hessenbergs, which are essentially the upper triangular is filled, and so is the subdiagonal. Um, and then proceed from there. There's also just your good old-fashioned regular method of diagonalization, wherein you take the definition of an eigenvalue and an eigenvector, which is essentially AV equals lambda V, right? You can rewrite that as A minus lambda IV equals 0. And then if you take the determinant of that matrix and solve for that, that would be equal to 0 because eigenvalues and eigenvectors exist. Um, do they? Eigenvalues and eigenvectors, they exist for, well, I mean, I guess they exist across the board in general, right? It's about discovering them, and these are all numerical methods to discover them. So, anyways, let's just stick with the cases of symmetric matrices where we can apply householder reflections and obtain a tridiagonal matrix. Now, how do you do householder reflections? Oh yeah, so you take the determinant. Sorry, I'm jumping back again. You take the determinant, equal it to 0. That's how you'll get all the eigenvalues, because once you open up that determinant formula, it becomes like a kind of a hairy polynomial that you can easily factorize. Uh, and then that factorization gives you the possible values, gives you all the possible eigenvalues, right? And then you take that and you utilize it with the x. You set. What do you do after that? And this is the thing I went over the previous video. I don't remember exactly. I'm just gonna focus on what I remember about householder diagonalizations, where a householder diagonalization is essentially you construct the matrix I minus 2 times the outer product of V, where V is defined as you take alpha. Okay, I can't remember this part. This part is the difficult part to remember from memory. So I think I'm going to call this video right now, and we'll get back to this tomorrow. And hopefully tomorrow we'll actually get to some code on the householder reflectors, because I feel like a good, instead of trying to see this whole thing end to end and understand it. I mean, that's one way to do it, but I think at this point, I myself am personally getting irritated with not writing any code. So I'm going to try and write some code, probably not a lot, at least write the inner product and outer product. Inner product we've done like hundreds of times. It's essentially just the dot product. It's a very easy piece of code to write in pure Python. Outer product I haven't done, but honestly, I think that will not be really a problem. Um, right? Would it be? Let's see. So we got, essentially doing the matrix multiplication again and again, right? Uh, yeah. And then, so the first element gets multiplied by the second element. This is the first element in the first one gets multiplied by the first element in the second one. That's the first element. Then the first element gets multiplied by the second element. That's the second element in the matrix. Then yeah, so I think this should be able to be done with like a kind of weird looking list comprehension, but I think it shouldn't be doable. It should totally, I mean, not only I think, I know for a fact. You know how I know for a fact? Because there's entire libraries that do this. So I'm obviously not doing anything that out there. It's more of a process I enter into for my own edification. So, anyways, promise for code tomorrow. Yes, we code. Have a great one, everyone. And, stay curious.